Hey guys, this is the beginning of Module 6 and we're going to start talking about systems of linear equations. So what a system of equations is it's just two or more equations. And the ones that we're going to work with in Algebra 1 are the ones that involve two equations. So when we are solving a system, we're going to come up with a solution. So what is a solution when I have two equations? So a solution to one equation is the value typically of x, but the value of the variable that makes that equation true. So for a system, the solution has to make both equations true. And we're going to look at kind of the graph representation of what that looks like today. So what it happens to be, the solution is a point. So remember, point is an x and a y. It's a point where the lines intersect. So the point where the lines cross is their solution. But how we check if something is a solution is we're going to follow these steps. We're going to plug in our x and y coordinates into both equations. So it has to satisfy both. So notice that's all caps there to really emphasize that. If both equations produce true statements, then this is a solution. If not, not a solution. So we're going to try this in the first example. We're going to check, is 4, 1 a solution? So 4 is my x and 1 is my y. I want to check it in both. So I'm going to do this first one here. So I'm plugging in 4 for x and 1 for y, and I'm checking, does that in fact equal 6? So 4 plus 2 times 1, so do my multiplication, I get 2 there. 2 plus 4 is 6. So this one it works, but it has to work in both equations to be a solution. So we got to check it here. So 4 for x, 1 for y, does that equal 3? And it does. So yes, because it satisfies both equations. All right, same thing here on the second one. So we're plugging in negative 1 for y, or excuse me, negative 1 for x and 2 for y this time. So negative 1 for x and 2 for y, checking, do we get 8 here? So here I get negative 2 plus 10. That does equal 8, so it works in the first equation. Let's check the second one. So 3 times negative 1 minus 2 times 2, does that equal 5? So negative 3, here I get 4, so negative 3 minus 4, that does not equal 5. That equals negative 7. So because this point didn't work in both equations, not a solution. All right, so now we're going to graph the lines to find the solution to the system. So this is the system. It's the two equations kind of together. Their solution is the point where these two lines intersect. So we just finished up all of our graphing with lines, so we're going to go ahead and graph these. So my y-intercept of the first equation is negative 3, so I'm going to put a point at negative 3 on the y-axis. And the slope here is 1, or 1 over 1, so I'm going to go up 1 over 1. For these equations, you guys, I think it's helpful to actually keep the pattern going just to make my line more accurate. So I'm going to keep that going. Up 1 over 1, up 1 over 1. So we want these lines to be really, really accurate. So even like using a ruler would probably be really good. I have one on hand. So using a ruler just to make our line really straight and make sure it's going through the nice points. The reason why we want it to be so accurate is because we want to know where does it intersect this other line. So if it's off by a little bit, that can make the intersection point a little harder to find. All right, now we're going to graph the second line. So its y-intercept is negative 1, and its slope is negative 1. So down 1 and over 1 this time. Down 1 over 1. So I can see just by doing the down 1 over 1, that is the point where they intersected, but I'm going to go ahead and draw my line here. Again, trying to make it pretty accurate. All right, so the point of intersection is this one right here. So the coordinates of that are 1, negative 2. So the solution is that ordered pair. That is the solution to this equation. We could check it just by doing what we did in those first two examples. I could plug in 1 for x and negative 2 for y, and if it's true in both, that just verified we found the right one. All right. Example 2, we're going to do the same thing. We're going to graph. Now, these are not in slope-intercept form, so we could either graph using intercepts or we could solve for y to get it in slope-intercept form. I'm going to go ahead and just move it into slope-intercept form. So this one, I'll rewrite it here. So we've got x plus y equals 0. I want to get y by itself, so I'm going to subtract x from both sides. So y minus anything is just that thing. So this turns into y equals negative x. So we can think about it as negative x plus 0 if we want. Y-intercept is going to be 0, and the slope is going to be negative 1. So this is one of the equations. So y-intercept of 0, slope of negative 1. So down 1 over 1. And again, I'm going to keep the pattern going just so I can make my line accurate. Using a ruler makes it even better. All right, there's our first line. All right, second line, same thing, and I'm going to do this one kind of over here, guys. So y minus 1, and I'm going to rewrite that. Instead of 0.5x, I don't like the decimals in there. I'm going to change it to 1/2. Just, I like the fraction for slope purposes. Getting y by itself, all I have to do is add 1. So I get y equals 1/2 x plus 1. So now there's my equation in slope-intercept form. So my y-intercept is positive 1, and my slope is 1/2. So up 1 over 2, up 1 over 2. And then if I go back this direction, it's down 1 and left 2. All right, so now when I connect these guys, we are going to find their point of intersection. All right, so this one we might want to estimate a little bit. And even though my lines are really accurate, I can see that sometimes it intersects not at a nice point. That's okay. So for this one, an estimation would be okay, you guys, since we don't have another method of solving. So this one maybe, even though my lines aren't perfect, maybe I would say negative 1/2, positive 1/2. Oh, and sorry, you can't see that. Scoot my page down here. All right, so negative 1/2, so left 1/2 and then up 1/2. And I'm just estimating on that. We're going to learn some other methods of solving that would help in cases like this too. But that drew my two lines, and the point of intersection is our solution. All right, we're going to do just a couple more here. Okay, so this one already in slope-intercept form, y-intercept of negative 1, slope of 1, so up 1 over 1. Okay. All right, this one I'm going to go ahead and add x to the other side so that it gets y equals positive x, and that's a positive 2. Y-intercept of 2, slope of 1. So up 1 over 1, that's going to keep going. All right, so we can see, you guys, that these lines are actually never going to intersect. They're what we call parallel. So, and notice what they had in common. Once I rewrote this, they both had a slope of 1. So, we're going to kind of add to this table down here. So, this is a no solution example. So, what is the solution? No solution is no intersection. So, a graph example is like what we just had, parallel lines. So, I'm just drawing a super rough sketch here. Parallel lines, they're never going to intersect. Well, what does the equation look like when that happens? They have the same slope. So if they have the same slope, they are not going to intersect. All right, now one solution we've already seen. Point where lines intersect. So any, oh, if I could spell intersect, there we go. So any intersection point. So as long as they intersect, that point is the solution. Okay? And the equation characteristics, they need to have different slopes. And that's really the most important thing. They just have different slopes. All right. Infinite solutions. Well, what does that look like? So I think we're actually going to get that here in this last example. So let's go ahead and graph these. Y-intercept of negative 1, slope of 1/2, so up 1 over 2. Okay. All right. Okay, I'm going to rewrite this one. So I'm going to go ahead and add x. So now I have 2y equals positive x minus 2. Now divide everything by 2, and remember there's like a 1 sitting there, so I'm going to divide that by 2 as well. So I get y equals 1/2 x minus 1. Well, look, I just produced the same exact equation. So obviously that's going to be the same exact graph. So essentially I would just end up graphing one line on top of the other. So because they are the same exact line, they're called coinciding lines when that happens. That's infinitely many solutions because I'm just graphing one line on top of the other and the lines are intersecting at every possible point. So coinciding lines on top of each other is what that means. Okay, and what that looks like is I'm going to draw like a shorter one on top so you can kind of see. So it's one line on top of the other. So there's two lines there, but they're one on top of the other. So same slope and same y-intercept. They were exactly the same. Okay, so that's what was true about the equations. All right, so solving systems by graphing. You're graphing the two lines and find where they intersect, but it's possible to have no intersection or to intersect the entire way and be coinciding. So those are kind of our three different options for solutions. When you have one solution, you must answer with an ordered pair, an x and y coordinate, which represents the point where they are crossing.